Welcome to the last section we're going to do on Unit 1. We've done so much already, haven't we? Let me get this great pen here. Creative pen. We've done this one. We've done this one. All of these we've done. And today we're going to be working with more problems. Okay, should be fun. We're going to go through several examples. This first one, a flight simulator has pilots traveling in a circular path. Okay, so that's good. We know it applies to what we've been studying. They're moving them very quickly so that they will experience g-forces. If the pilots are traveling at 400 miles per hour, that would be a linear velocity, wouldn't it? 400 linear units per time, miles per hour. The circular room has a radius of 25 feet. All right, so find the number of rotations that the simulator makes per second. So I'm going to want omega in terms of rotations per second. Well, let's analyze this. For what I'm starting with, I'm going to have to do an interim, aren't I? I'm going to have omega, which is linear velocity divided by radius. I'm going to have to figure out what the units are going to be. I'd prefer to look at this way. That's the same as v times 1 over r. And then I can look at my units first. Let's do a units analysis. I'll do this with a purple pen. So I'm starting out with miles per hour. And I'm going to want to translate that into radians, because before I go to rotations, I've got to go to radians. I've got to get to radians per second. Okay. And I've got, what do I have right now? I've got 1 over 25 feet. So let's get it all into feet, which means I'm going to have to write that 1 over feet. I'm going to have to get miles into feet, which is easy enough. I'll do feet here. This is my conversion factor. Miles. And I'm going to go from hours, which I've got down here, get rid of those, to seconds. So these are my conversion factors I have to put into my equation. Let's go ahead and do it. angular velocity will be 400 miles per hour times the reciprocal of r, right? 1/25. And then my conversion factors are right here. I'm going to have to multiply this times 500, excuse me, 5,280 feet. And my other conversion factor, 1 hour is how many seconds? 300, oh, excuse me, can I make the same mistakes? 3,600 seconds in 1 hour. So there are both my conversion factors. And now that I've done that, I've taken care of that, I've taken care of that, I've taken care of that. I'm going to get my answer here in, my first answer is going to be in radians. So I'm going to have radians per second is what I'm going to come out with first. We're going to take care of that in a moment. Let me pull over my calculator and do all these calculations. So I've got 400, turn it on, 400 divided by 25 times 5280 divided by 3600. So this would be 23.67 radians per second. We know, of course, that I don't want my answer to be in radians. What was the question asking for? Rotations. How do I go from radians to revolutions or rotations? I'm going to put radians in the denominator and revolutions or rotations in the numerator. So my 23 point, oh, I wrote that wrong. It was 467. 467. My conversion factor is going to be 1 revolution per every 2 pi radians. And this will give me rotations per second. You pull over my calculator, I've still got that number in front of me. I just have to divide it by 2 and divide it by pi. So it says 3.73, we'll say. Call that our answer. 3.73 rotations per second. On to our next example. Remember now, with examples, you can turn me off. Maybe turn the sound right down and just sit there and work in your workbook. And then you can check back here towards the end of it and see if you got the same answer I did. Hopefully, I will have gotten it right. A large clock has its seconds hand traveling at 2.5 inches per second. Find the length of the second hand. All right. So I have a linear velocity of 2.5 inches per second. What else do I know? I want the length of the second hand. So that's what I'm looking for, r. What does r equal? And we'll probably express that in inches, don't you think? What do I know about the angular velocity? Well, my knowledge of time can help me with this, I think. What do we know? We get 1 revolution per minute, true? So we have 1 revolution per minute. That's good that we know that, because now we can perhaps use this formula. We can actually divide both sides by omega, right? We could say r is going to equal the linear velocity divided by the angular velocity. And we want to make sure that our units are good. We are not, in our formula, going to be able to use 1 revolution per minute. We have to use radians. So what would this be? It wouldn't be 1 revolution, it would be 2 pi radians per minute. That's what we want to use in this formula. So let's try it. My velocity is in inches per second, 2.5. That sounds okay, doesn't it? Oh, but my angular velocity is in minutes. I'd probably better change that to seconds. What do I have to do to get that into seconds? 2 pi. I've got to say 1 minute divided by how many seconds? 60 seconds. So it'll be 2 pi divided by 60, and the minutes will cross out, and I'll have radians per second. Now I've got the right units, seconds for linear and seconds for angular, so I can proceed with my calculations. We've got 2.5 divided by 2 pi over 60. Remember that stay, change, flip. I'm going to stay the same with the numerator, 2.5. That was a point. And then I'm going to change. I'm going to change from dividing to multiplying. And take the reciprocal of this. Stay, change, flip. So we have 60 over 2 pi. And I'll pull my calculator up to help me out with this. Turn it on. 60 divided by 2 divided by pi, and then times 2.5. I think I've accounted for everything. 2.5 times 60 divided by 2 and divided by pi gives me equals 23.87 inches. I hope that's what you got as well. If not, look at those units. The formula is actually very straightforward. It's just you have to make sure you have your units correct. The last one we're going to do is right here. We've got 2 gears connected by a belt. Let's do a little picture of this. We've got, I'm not putting the teeth on the gears. You know it has teeth, right? and connected by a belt. What would that look like? Something like this. There's my belt going around this thing. The large gear, that's this one, has a radius of 6 inches, while the small gear has a radius of 3 inches. If a point on the small gear, so let me get another color. So let's say this point right here, one of the gear teeth perhaps. A point on the small gear travels at 16 revolutions per minute. What's the angular velocity of the large gear? So here we have a linear velocity. Now the linear velocity of both of these, oh, excuse me, no, this is an angular velocity, but the linear velocity of both of these has to be the same, doesn't it? Because the belt has them connected. So whatever that linear velocity is, it's going to, we can use this formula here. The angular velocity of the small times the radius of the small one, and it also equals the angular velocity of the large one times the radius of the large one. We know both the radii, so I could set, since these are both equal to v, I could set them equal to each other. Omega small, and what was the radius here? Well, the small one was 3, so let's do it this way. And the radius of the large one was 6. And I do know, let's see, that this small gear, its angular velocity is 16 revolutions per minute. 16 revolutions per minute. So the ratio between these two we can figure out. I'm going to divide both sides by 6, and I get an angular velocity here. Maybe I can see. That would give me 2. That would give me 8. Is 8 revolutions per minute. Find the angular velocity of the large gear. Here's one I threw in because I like it. Albert Juarez's truck has wheels which are 36 inches in diameter. So what is the radius then? We know that's what we're going to be interested in. 18 inches. If the wheels are rotating at 630 revolutions per minute, find the truck's speed in miles per hour. Okay. Truck speed. So we're looking at we want to find the linear velocity, and the formula for that was the angular velocity times the radius. Whoops, went the wrong way. The angular velocity, okay, we're going to want to convert this into, instead of revolutions per minute, we're going to want, that's right, radians per minute. So we've got 630 revolutions per minute, and our conversion factor, we have 1 revolution here and 2 pi radians here. So this would convert it now into radians as we need to, and the only other thing we have to do, we have to multiply it times 18. Let me just make a note of what I'm doing here. Sometimes I think it might not be that clear. So this is our angular velocity in revolutions per minute. This is our conversion factor. And let's make it clear what we're doing. From revolutions to radians. And of course this is the radius. We pull over our calculator. We'll do this. We get 630 times 2 pi times 18, and we end up with, let me get that back. Oh, 71,364.4, we'll say. But what are my units of measure here? I'm working in inches and minutes. So that's inches per minute. That's not what we want to know. We want to know miles per hour. So I need some more conversion factors here, don't I? So we'll take what we have and we'll put in the proper conversion factors. We want to go from inches to miles, and I'm going to do that in 2 steps. From inches to feet, so that would be 12 down here, wouldn't it? And a 1 up here. And then from feet to 2 miles. What else do we have to convert? Oh, from minutes to hours. So from 60 minutes per 1 hour. I didn't write the units here. I should have. I had inches per minute. When I do this, let's see how it cancels out. We get the inches taken care of, feet taken care of, minutes. Ooh, I did the minutes wrong, didn't I? Should be 60 minutes per 1 hour. That's an easy mistake to make, isn't it? Wow, glad we checked it. Minutes. And that will leave me with miles per hour. So let's see if we can do these numbers. 71364.4. We're going to divide by 12. We're going to divide by 5,280. And we're going to multiply by 60. Let's see what we get. So I've got this number right here. I'm going to multiply it times 60. I'm going to divide it by 12. I'm going to divide it by 5,280. Those are all my conversions to get it into miles per hour. This says he is going 67. Let's call it 67.6 miles per hour. How's that? Close enough? Miles per hour. Let me check that against my own calculations earlier. And that looks really good. So I'm just going to box my answer. That will end this unit. You're going to do this homework when you get back in class with me. See you then.